Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
Beyond the thin veil of Earth's atmosphere, the sky opens into a depth that has no edge and no center. Light travels across this depth for spans of time that exceed the history of any species that has learned to look upward. Stars appear fixed to the eye, yet each one is in motion, carried by the slow rotation of a galaxy that itself drifts among other galaxies. The background against which all observations take place is not empty. It is filled with radiation left from the early universe, with dust scattered between stars and with faint objects that reflect or emit only the smallest fraction of the light that reaches them. Astronomy begins in this outermost context. Telescopes do not first encounter individual objects but fields. Each field is a layered record of distance, where closer bodies move perceptibly over days or weeks, while distant stars remain nearly still. The sky is therefore both a map and a process. It changes continuously, though often too slowly for casual notice. The work of detection depends on recognizing change within apparent stillness. At the larger scale, the Milky Way forms a flattened disk of stars, gas, and dust, with spiral structure shaped by gravity and rotation. The solar system lies within this disk, embedded in one of its quieter regions. From Earth, the band of the galaxy stretches across the night sky, marking a direction of greater stellar density. Yet most modern surveys do not privilege this band alone. They sweep large portions of the sky repeatedly, collecting light from many directions in a steady rhythm. Against this immense backdrop, small bodies are difficult to see. Asteroids and comets reflect sunlight, but their surfaces are dark and their sizes are limited. At great distances, they appear only as points of light indistinguishable at first glance from stars. What separates them is motion. A nearby object shifts position relative to the fixed background as Earth and the object move along their respective paths. Detecting such motion requires comparison, patience, and precise measurement. The outer sky is therefore a place of contrast. It holds structures that span hundreds of thousands of light years, and also objects no larger than a city. Both are governed by the same physical laws, yet their effects unfold on different scales. Gravity shapes the paths of stars and planets alike, while light carries information from each to the instruments that observe them. The farther the source, the older the information, and the more the present depends on records of the past. Interstellar space lies between stars filled with gas so sparse that it would be considered a vacuum by terrestrial standards. Within this space, objects can travel for millions of years without encountering a star system. Some may originate near distant suns altered by close passes or stellar evolution, then ejected into the wider galaxy. Their journeys are long and mostly uneventful, marked only by gradual changes in velocity as they respond to the combined gravitational influence of many stars. From Earth, such travellers are almost invisible until they approach the inner regions of a planetary system. Only then does reflected sunlight increase enough for detection. Even so, discovery often occurs after the object has already crossed much of the region where planets orbit. The sky, vast as it is, offers only brief windows during which faint, fast-moving bodies can be noticed. The background sky also contains noise. Cosmic rays strike detectors. Atmospheric effects blur images. Instrumental imperfections introduce patterns that must be separated from genuine signals. The task of astronomy is not merely to observe, but to filter. What remains after filtering is treated cautiously, compared against expectations, and tested through repetition. In this setting, the appearance of an unfamiliar moving point does not immediately imply significance. The sky produces countless such points. Most are catalogued, their orbits refined until they become predictable. Some fade from view as they recede or as observing conditions change. Only a few persist as questions. The designation. 3. I-Atlas arises within this outermost frame, where naming follows detection rather than understanding. At this stage, the object is defined only by its presence against the star field and by its measured positions over time. Its deeper nature remains unexamined. The outer sky offers no commentary, only data. Light arrives, is recorded, and is stored. Meaning is not assigned here. It is postponed. In the distant sky there is no intent, no direction, only motion governed by physical law. Any appearance of purpose emerges later within interpretation. At this first level, the object exists as a trace, a moving point embedded in a universe that is already in motion everywhere. The task remains to narrow the focus step by step without leaving this broader context behind. From the wide and indifferent sky, attention moves inward to the instruments that attempt to measure it. These instruments are built on Earth, constrained by gravity, atmosphere, and human design, yet they extend perception far beyond unaided sight. Modern sky surveys rely on telescopes that scan large areas, repeatedly recording light, with electronic detectors rather than photographic plates. Each exposure captures a moment, and the sequence of moments allows motion to be separated from stillness. The principle is simple, but its execution depends on precision across many layers of technology. Telescopes used for survey work are optimized for coverage rather than detail. Their mirrors are shaped to gather as much light as possible over a wide field of view. The detectors, usually charge-coupled devices, convert incoming photons into electrical signals. Each pixel records the accumulated signal during an exposure, producing a grid of values that represent brightness across the field. This raw data is not yet an image in the familiar sense. It must be corrected for instrumental effects, calibrated against known reference stars and aligned with previous observations. The atmosphere sits between telescope and sky, altering the light that passes through it. Turbulence causes stars to blur and shift slightly, an effect known as seeing. Water vapor and other gases absorb specific wavelengths. To reduce these influences, surveys often observe from high-altitude sites, where the air is thinner and drier. Even so, atmospheric effects cannot be eliminated entirely. They are measured, modelled, and compensated for during data processing, but residual uncertainty remains part of every observation. Time is a critical factor. Surveys are designed to revisit the same region of sky after known intervals, sometimes minutes, sometimes days. By comparing images taken at different times, software searches for points of light that have changed position or brightness. Most detections are automated. Algorithms flag candidates based on predefined criteria, such as consistent motion across multiple frames. Human review follows, but only after the data has been reduced to manageable form. The sensitivity of a survey determines how faint an object it can detect. This depends on mirror-size detector efficiency, exposure time, and background noise. Faint objects require longer exposures, but longer exposures increase the chance that motion will blur the signal. Survey designers balance these factors based on their goals. Objects moving rapidly across the sky may require shorter exposures and more frequent revisits, while distant, slow-moving objects can be tracked with longer integrations. Catalogues play a central role. Known stars and galaxies are mapped with high precision, forming a reference, against which new detections are compared. When a point of light does not match a catalogued object and shows motion, it is marked as potentially new. Initial measurements are rough. Positions are recorded relative to background stars and uncertainties are calculated. At this stage, an object's identity is provisional. Many candidates are later linked to known bodies whose predicted positions were uncertain or outdated. Data flows from telescope to storage to analysis pipelines. Each step introduces potential sources of error. Electronic noise, cosmic ray hits, and detector defects can mimic real objects. Software attempts to recognize and discard such artifacts, but it does not succeed perfectly. For this reason, confirmation requires repeated detection across independent observations. An object must be seen moving consistently in a way that matches physical expectations. The naming of an object like 3i Atlas reflects this process. The designation indicates that it is the third object in a particular category, detected by a survey system associated with the name Atlas. At this stage, the name carries no implication about origin or nature beyond classification. It is a label attached to a set of measurements, not a description of behavior. Survey instruments do not interpret intent. They measure brightness, position, and change. Any suggestion of unusual behavior must first survive scrutiny at the level of instrumentation. Analysts ask whether the motion could arise from measurement error, from misidentification of reference stars, or from known effects such as parallax caused by Earth's own movement. Corrections are applied for Earth's rotation and orbit, transforming observed positions into a common frame of reference centered on the solar system. Only after these corrections can motion be compared meaningfully with models. At this point, the role of the instrument recedes slightly, but its influence remains embedded in the data. The limits of resolution and sensitivity define what can and cannot be known. An object smaller than the detection threshold leaves no trace. An object moving too quickly may be observed only briefly. The sky filtered through instruments is always incomplete. The inner edge of this region is reached when measurements are stable enough to be used for further analysis. The telescope has done its work. The data now represent positions in space and time with quantified uncertainties. What remains is to connect these positions into a path using established physical laws. Before that step, however, the instruments themselves must be trusted. Calibration stars are checked. Independent surveys are consulted when available. Agreement across systems increases confidence that the signal is real. In this way, the outer sky is translated into numbers by machines designed to be repeatable and impartial. The process strips away context and leaves a moving point with coordinates and timestamps. The appearance of purpose or deviation has not yet emerged. There is only detection, measurement, and the careful narrowing of uncertainty. From here, attention can move inward from tools to trajectories, carrying with it the quiet constraints imposed by the instruments that first made the object visible. Within the steady flow of survey data, the first detection of 3i Atlas does not arrive as an announcement, but as a deviation. In a sequence of images taken of the same star field, a faint point of light shifts slightly between exposures. The shift is small, measured in fractions of an arcsecond, yet it is consistent. Against the dense and largely unmoving background of stars and galaxies, this point does not return to the same coordinates. The software flags it, assigning a provisional identifier and recording its positions with associated uncertainties. At this stage, the object is not yet distinguished from many others detected each night. Survey pipelines process thousands of candidates, most of which are later rejected. Some correspond to known asteroids whose predicted positions were imperfect. Others are artifacts caused by detector noise or cosmic ray strikes. The first task is therefore confirmation. The same region of sky is examined in additional images taken within the same night and on subsequent nights. If the point of light continues to appear and continues to move in a coherent way, its status changes from candidate to object. 3i Atlas persists. Its motion is measured across multiple observations, each one adding a data point. The positions form a short arc insufficient at first to define a precise orbit, but adequate to show that the object is not fixed. The brightness remains near the detection threshold, fluctuating slightly within expected limits given atmospheric conditions and measurement noise. No extended structure is visible. It appears as a point source unresolved by the survey telescope. The act of detection is bound to timing. The object is found not at the moment it enters the inner solar system, but at the moment its reflected light becomes detectable against the background. This moment depends on distance-size surface properties and viewing geometry. An object approaching from a direction near the Sun may remain hidden longer lost in glare. One approaching from a darker region of sky may be seen earlier. The detection of 3i Atlas therefore represents an intersection of circumstance rather than a beginning. Once confirmed as real, the object's positions are submitted to a central database used by the astronomical community. Other observers are alerted and independent measurements are sought. Additional telescopes, some with greater sensitivity or different observing schedules, attempt to recover the object. Each successful recovery reduces uncertainty. The motion is compared across datasets and systematic differences are examined. Agreement suggests that the measurements reflect the object's true path rather than instrumental bias. The early data define a trajectory relative to Earth, not yet corrected fully for the planet's own motion. Apparent motion across the sky includes contributions from the object's velocity and from parallax caused by Earth's orbit. Initial calculations remove the most obvious effects, transforming observed positions into a heliocentric frame. Even then, the arc is short. Many different orbits could fit the data within uncertainty bounds. The goal at this stage is not explanation, but constraint. The designation 3i Atlas is formalized as the object meets criteria for continued tracking. The label encodes its discovery sequence and survey origin. It does not describe composition origin or behavior. Such information lies beyond what the early observations can support. The name simply allows consistent reference as more data accumulate. As observations continue, the object's motion begins to suggest a high velocity relative to the Sun. This impression arises not from a single measurement, but from the rate at which its position changes across the sky over days. The background stars provide a stable frame. Against them, 3i Atlas moves faster than many typical main belt asteroids. This alone is not unprecedented. Near-Earth objects can exhibit rapid apparent motion, especially when close to Earth. The distance to the object is therefore a critical unknown. Brightness measurements provide limited clues. Assuming a typical reflective surface, a faint object could be small and nearby or larger and farther away. Without direct distance measurements, brightness does not resolve the ambiguity. No clear signs of a coma or tail are detected in the survey images. This absence is noted, but it is not decisive. Some comets show little activity at large distances. Others are depleted of volatile materials. The detection record remains neutral. During this phase, caution governs interpretation. The scientific process resists narrative. Analysts focus on refining measurements, checking consistency, and extending the observational arc. Each new data point slightly reshapes the range of possible paths. Some initial orbital solutions are discarded as incompatible with later observations. Others remain viable. The object's future positions are predicted with uncertainty ranges guiding follow-up observations. The first detection thus marks a transition from anonymity to attention. Before detection, the object moves unseen through space. After detection, it enters a network of measurement, calculation, and comparison. Yet it remains at this stage an abstract entity defined by coordinates and times. Its physical reality is inferred, not experienced. There is no image that reveals surface texture or shape. There is no spectrum detailed enough to indicate composition. Those possibilities lie beyond the reach of the initial survey data. What distinguishes this detection from countless others is not yet clear. Many objects are discovered each year with unusual preliminary properties that later resolve into familiar categories. The early behavior of 3I Atlas does not immediately demand special treatment. It simply does not settle quickly into known patterns. Its motion resists rapid classification, and so it remains under observation. The region defined by first detection ends when the object's existence and basic motion are no longer in doubt. That threshold is crossed as repeated observations confirm consistency across instruments and nights. The object is now part of the measured sky. It carries with it a growing record of positions that can be connected into a path. The focus can now move inward from the fact of motion to the attempt to describe that motion within established frameworks. With the object confirmed and its positions accumulating, attention turns inward to orbital context where motion is described using established mechanics rather than impression. An orbit is not observed directly. It is inferred from a sequence of positions measured against the background sky, each one stamped with a time and corrected for known effects. From these, a path is calculated that best fits the data within uncertainty limits. This path is provisional and subject to revision as new observations extend the arc. The first step is to place the object in a heliocentric frame, removing the influence of Earth's rotation and its annual motion around the Sun. What remains is the object's motion relative to the central mass of the solar system. Classical mechanics provides the framework. Under the assumption that gravity dominates an object's path can be described by a conic section, such as an ellipse, parabola, or hyperbola. Each form corresponds to a different balance between velocity and gravitational binding. Early solutions for 3I Atlas rely on short arcs, sometimes spanning only a few days. With such limited coverage, many orbits can fit the data almost equally well. The calculations produce a family of possible trajectories rather than a single definitive path. Analysts examine this family to identify common features. One such feature is the object's incoming direction relative to the plane of the planets. Another is the speed implied by the curvature or lack of curvature in the observed motion. The curvature of an orbit reflects acceleration caused by gravity. A bound object, such as an asteroid in an elliptical orbit, shows noticeable curvature as it responds to the Sun's pull. An unbound object moving faster than the escape velocity at its distance follows a hyperbolic path that bends only slightly. Detecting this difference requires precise measurements over time. In early data, curvature may be masked by uncertainty, making classification tentative. Calculations suggest that 3I Atlas is moving at a velocity that is high compared to many solar system bodies at similar distances. This inference is cautious. Velocity is derived from angular motion combined with estimated distance. Distance itself is uncertain at this stage. Small changes in assumed distance lead to significant changes in inferred speed. Analysts therefore explore a range of distances consistent with the data calculating corresponding velocities and orbital shapes. The orbital plane is also examined. Most planets and many small bodies orbit close to a common plane defined by the solar system's formation. Objects with orbits highly inclined to this plane are less common but not unknown. The preliminary orbital solutions for 3I Atlas indicate an inclination that is not closely aligned with the planetary plane. This alone does not imply an external origin. Long-term gravitational interactions can tilt orbits over time. The observation is noted, not emphasized. Uncertainty is quantified explicitly. Each positional measurement carries an error ellipse reflecting limits imposed by instrument resolution and atmospheric conditions. These errors propagate through orbital calculations, producing uncertainty regions for future positions. Predictions are expressed as ranges rather than points. Follow-up observations are planned to intersect these ranges, refining the orbit by eliminating solutions that fail to match reality. As data accumulate, some candidate orbits are discarded. Solutions that predict positions inconsistent with new observations are removed from consideration. The remaining solutions converge gradually. The object's past path is traced backward in time within these models, while its future path is projected forward. Backward integration suggests where the object came from relative to the Sun, while forward integration indicates where it is going. Both directions are treated symmetrically with equal attention to uncertainty. In this context, the term interstellar has a specific meaning. It refers to an object whose orbit is not bound to the Sun, implying that it originated outside the solar system and will not remain within it. Determining this requires showing that the object's velocity exceeds the local escape velocity, even when uncertainties are considered. Early indications for 3I Atlas approach this threshold, but do not immediately cross it decisively. Analysts refrain from definitive statements until the margin is clear. Gravitational influences beyond the Sun are also considered. Planets, especially the more massive ones, can alter the paths of small bodies during close encounters. The calculated orbit is examined for potential past or future planetary interactions that could explain its current motion. At this stage, no close approach is evident within the observed arc. The object's path appears smooth, without abrupt changes that would suggest recent strong perturbations. The role of assumptions is acknowledged. Orbital calculations often begin by assuming purely gravitational motion. This simplifies the mathematics and provides a baseline. Deviations from this baseline are addressed later, once the gravitational solution is well constrained. For now, the goal is to determine whether gravity alone can account for the observed positions within error bounds. The provisional orbit places 3I Atlas on a trajectory that carries it through the inner regions of the solar system on a timescale of months rather than years. This inference comes from extrapolating the fitted path forward. The timing is uncertain, but it provides a framework for planning observations. Telescopes are scheduled to monitor the object as long as it remains observable, extending the arc and reducing ambiguity. At this level of analysis, language remains restrained. Terms such as unusual or unexpected are avoided. The orbit is described in quantitative terms compared against known distributions of small body orbits. Where it lies near the edge of these distributions, this is stated without emphasis. The focus is on placement, not interpretation. The inner boundary of this region is reached when the orbit, though still provisional, is stable enough to serve as a reference for further comparison. The object now has a defined path relative to the Sun, expressed through parameters that can be updated as new data arrive. Motion is no longer merely observed, it is modelled. With this model in place, attention can move inward again from the shape of the path to expectations formed by prior knowledge of similar paths. With a provisional orbit established, the next inward step is comparison, placing the object's motion alongside expectations drawn from known populations of small bodies. The solar system contains many classes of such bodies, each with characteristic behaviours shaped by formation, history, composition, and environment. Asteroids in the main belt move on relatively stable low eccentricity orbits between Mars and Jupiter. Near-Earth objects follow paths that bring them closer to the Sun and to Earth, often with higher eccentricities and a wider range of inclinations. Comets originating from colder outer regions display activity as they warm, releasing gas and dust that can alter their motion slightly. Expected behaviour is not a single pattern but a range. Gravity dominates the motion of all these bodies, producing predictable trajectories when averaged over time. Deviations occur, but they tend to fall within understood limits. For asteroids, these deviations are usually small, arising from weak thermal forces or distant planetary perturbations. For comets, non-gravitational effects can be more pronounced, especially when volatile materials sublimate unevenly from the surface. In the outer solar system, beyond the orbit of Neptune, icy bodies move slowly, their activity subdued by low temperatures. As they approach the Sun, solar heating increases. Ice transitions directly from solid to gas, a process known as sublimation. The escaping gas carries dust with it, forming a coma and sometimes a tail. The reaction force from this outflow can produce measurable changes in velocity. These changes are generally modest and vary smoothly with distance from the Sun. For an object like 3I Atlas, expectations are initially framed by analogy. If it is an asteroid, it should show little to no activity and follow a trajectory determined almost entirely by gravity. If it is a comet, activity may become detectable as it approaches warmer regions accompanied by slight non-gravitational accelerations. If it is an interstellar object, its inbound velocity relative to the Sun may be higher than typical bound objects, and its orbit may be hyperbolic. The expected inbound speed for bound solar system objects at large distances is limited by the Sun's gravitational well. Objects formed within the solar system tend to share the Sun's motion through the galaxy, resulting in relative velocities that cluster within a certain range. An object arriving from interstellar space would not share this motion, and could therefore approach with a higher relative speed. Even so, the distribution of stellar velocities in the local region sets an upper bound. Extremely high speeds would be inconsistent with known galactic dynamics. Inclination offers another comparison. The majority of small bodies have orbits clustered near the plane of the planets. High inclination objects exist, including some that approach perpendicular or even retrograde orientations, but they are less common. The expected distribution reflects both the conditions of formation and the long-term effects of gravitational interactions. An object with a markedly different inclination draws attention not because it is impossible, but because it is statistically rarer. Brightness behavior also carries expectations. For an inert body, brightness changes primarily due to changing distance from the Sun and Earth, following an inverse square relationship. For an active comet, brightness can increase more rapidly as activity begins, sometimes showing asymmetries or sudden changes. The absence of such behavior at a given distance does not rule out a cometary nature, but it informs expectations about composition and volatile content. In established populations, these behaviors are well characterized through decades of observation. Models exist that predict how objects should move and brighten as functions of distance and time. When an object's observed behavior falls within these modeled ranges, it is classified accordingly. When it falls near the edges, classification becomes tentative. Only when behavior consistently lies outside known ranges does it prompt deeper scrutiny. For 3i Atlas, the expected behaviors derived from preliminary orbital parameters suggest several possibilities without favoring one decisively. Its apparent speed is higher than average for many known asteroids, but not yet conclusively beyond the bound range when uncertainties are considered. Its inclination is notable but not unique. Its brightness remains low and steady, consistent with an inert body at its inferred distance. The expectation for gravitational motion is smoothness. Over short timescales, the path should be well approximated by a conic section. Small deviations may appear as residuals when observations are compared to the best-fitting orbit. In known objects, these residuals often correlate with known effects, such as solar radiation pressure acting on very small bodies or outgassing forces in comets. The magnitude and direction of these residuals provide clues about underlying processes. Another expectation concerns rotation. Although rotation is not directly observable in early detection data, it influences activity patterns. A rotating body with localized active regions may produce periodic variations in brightness or acceleration. Such patterns, if present, tend to emerge gradually as more data accumulate. Their absence in early data is typical and does not carry strong implications. In terms of physical survival, expectations are shaped by thermal stress. Objects approaching the Sun experience increasing temperatures. Fragile bodies may fragment or shed material, altering both brightness and motion. Robust bodies may remain intact. The distance at which such changes occur depends on composition and structure. Observations at large distances therefore provide only limited constraints. The expectation framework is intentionally conservative. It defines what is normal before considering what is unusual. Analysts compare the object's properties against distributions, not against narratives. Statistical rarity is quantified where possible. A property that lies several standard deviations from the mean of a known distribution may be flagged for attention, but even then alternative explanations are sought. At this stage, 3i Atlas does not violate expectations in a singular way. It occupies a region of parameter space that is sparsely populated but not empty. This placement invites continued observation rather than immediate reinterpretation. The scientific process values patience, allowing time for patterns to emerge or dissolve as data improve. The inner boundary of expected behaviors is reached when the object's observed properties are sufficiently defined to test specific hypotheses. Before that point, expectations serve as a backdrop rather than a verdict. They frame questions rather than answer them. With this framework established, attention can move inward again from general expectations to the detailed examination of how the object's behavior compares with them in practice. With expectations established, analysis turns inward to the deviations themselves, defined not as anomalies, but as measurable differences between observation and model. Deviations are not judged by impression. They are expressed as residuals, the small discrepancies that remain when observed positions are compared with positions predicted by a purely gravitational orbit. In well-behaved cases, these residuals scatter randomly around zero, reflecting measurement noise. When they show structure, direction, or persistence, they invite closer examination. For 3i Atlas, early residuals do not vanish as additional data are added. They remain small, but they do not distribute evenly. Over successive nights, the object appears slightly ahead of or behind its predicted position, along the fitted path depending on the solution used. Adjusting the orbit reduces some discrepancies but introduces others. This behavior suggests that a single simple gravitational model may not capture all influences acting on the object. The magnitude of these deviations is subtle. They are measured in arcseconds, translating to distances that are small compared with the scale of the solar system. Such differences are common in the early tracking of many objects and often disappear as the orbit is refined. The distinguishing feature here is persistence. Even as the observational arc lengthens, the residuals do not collapse fully into random scatter. They retain a weak but coherent pattern. One possible explanation is remaining uncertainty in distance. If the object is slightly closer or farther than assumed, the inferred velocity and acceleration will be affected. Analysts test this by exploring alternative orbital solutions within uncertainty bounds. Some solutions reduce the residuals temporarily, but none eliminate them entirely without creating inconsistencies elsewhere in the data. The deviations shift rather than disappear. Another possibility lies in timing. Errors in timestamps, though rare, can introduce systematic offsets. These are checked against independent clocks and cross-reference between observatories. No discrepancies large enough to account for the observed pattern are found. Instrumental calibration is reviewed again. Reference star catalogues are verified. The residuals persist beyond these checks. Brightness behavior is examined alongside positional data. If the object were undergoing episodic activity, small changes in brightness might correlate with changes in motion. At this stage, brightness remains largely steady with variations consistent with changing geometry and measurement noise. There is no clear evidence of sudden outbursts or fading that would point directly to active mass loss. The direction of the deviation is particularly important. Non-gravitational forces, if present, tend to act along specific vectors. Outgassing forces usually act roughly opposite the direction of the escaping material, often aligned with the Sun-object line. Radiation pressure acts away from the Sun and is more effective on small low-mass objects. Thermal forces such as those arising from uneven heating produce accelerations tied to the object's rotation and surface properties. For 3I Atlas, the residuals appear to align weakly with the object's direction of motion rather than purely radial from the Sun. This observation is tentative and subject to revision, but it guides further analysis. Forces aligned with motion can either speed up or slow down the object slightly relative to a gravitational trajectory. Such effects are known in cometary dynamics, but are usually accompanied by visible activity. The absence of visible activity complicates interpretation. It does not exclude non-gravitational forces, but it narrows the range of plausible mechanisms. Very low-level outgassing could occur without producing a detectable coma, especially if the gas is transparent or the dust production is minimal. Alternatively, thermal forces can act on inert bodies if their surfaces have uneven reflectivity or conductivity. These forces are typically weak but can accumulate over time. Statistical tests are applied to the residuals. Analysts assess whether the pattern could arise by chance given the noise level. The probability is low but not negligible. In scientific terms, the result is suggestive rather than conclusive. It justifies continued attention but not a change in classification. The deviations are documented carefully with error bars and assumptions clearly stated. Historical comparisons provide context. Other objects have shown similar early deviations that later resolved as data improved. In some cases, what appeared to be non-gravitational behavior was later traced to underestimated uncertainties or to subtle biases in the reference star catalogue. In other cases, genuine non-gravitational accelerations were confirmed, often linked to cometary activity that became visible later. The key distinction lies in scale and consistency. For 3i Atlas, the deviations are consistent in sign over several observation windows. They do not reverse randomly. This consistency suggests an underlying cause rather than noise, but the cause remains undetermined. The deviations are also small enough that they could be overwhelmed by future data, or altered by improved modelling. Analysts refrain from attributing intent or purpose. The language used remains mechanical. The object is described as exhibiting a small systematic deviation from a purely gravitational trajectory. This phrasing carries no implication beyond measurement. It avoids anthropomorphic interpretation and keeps the focus on physical processes. The temporal evolution of the deviations is monitored. If they increase as the object approaches the Sun, that trend would support certain mechanisms over others. If they diminish or change sign, alternative explanations would gain weight. At this stage, the dataset is still too limited to establish a clear trend. The region of deviations is bounded by observation quality. As long as uncertainties remain comparable to the deviations themselves, interpretation remains provisional. The scientific approach is to accumulate data until the signal-to-noise ratio improves. Only then can deviations be modelled with confidence. As this region closes, the object stands at an intermediate point. It behaves almost as expected, yet not entirely. The differences are not dramatic, but they are persistent enough to resist dismissal. They form the narrow bridge between routine classification and deeper inquiry. With these deviations, characterized but not explained attention can move inward again from observed mismatch to the examination of how confidently those observations can be trusted. Before any deviation can be treated as physically meaningful, the question of confidence moves to the foreground. Measurement confidence is not a single value, but a layered assessment that spans instruments, methods, and assumptions. Each recorded position of 3i Atlas represents a convergence of many processes from the arrival of photons at a detector to the mathematical treatment that converts raw signals into coordinates. Understanding how uncertainty enters at each step is essential to judging whether observed patterns reflect the object or the system that observes it. Positional uncertainty begins with the detector. Charge-coupled devices record light in discrete pixels, each with finite size. The centroid of a point source is estimated by fitting a model to the distribution of brightness across neighbouring pixels. This estimation is limited by signal strength, background noise, and the sharpness of the image. Faint objects near the detection threshold produce broader uncertainty because fewer photons define their position. 3i Atlas, being faint in early observations, carries this limitation inherently. Atmospheric effects add another layer. Turbulence causes stars to wander slightly during an exposure smearing the image. Although short exposures reduce this effect, they also reduce signal. The resulting compromise means that every measurement contains a small variable atmospheric component. Observations taken from different sites experience different atmospheric conditions, introducing subtle variations that must be reconciled during analysis. Reference frames are another source of uncertainty. Positions are measured relative to background stars whose own coordinates are taken from catalogues. These catalogues are highly precise but not perfect. Small systematic errors in star positions propagate directly into object measurements. Over wide fields, optical distortions in the telescope can also introduce position-dependent biases. Calibration routines correct for these effects, but residual distortions remain at a low level. Timekeeping enters next. Each exposure is stamped with a time that must be accurate to fractions of a second. Errors here translate into positional errors for moving objects. Observatory clocks are synchronized to international standards, and cross-checks are routine. For 3, IATLAS timing accuracy is verified across multiple observatories, reducing the likelihood that time errors contribute significantly to the observed deviations. Data reduction pipelines apply corrections automatically. Bias subtraction removes electronic offsets. Flat fielding corrects for pixel-to-pixel sensitivity differences. Cosmic ray rejection identifies and removes transient signals. Each step relies on assumptions about detector behavior. When those assumptions hold, the corrections improve accuracy. When they fail, they can introduce subtle biases. For this reason, analysts often reprocess critical observations, manually testing alternative reduction parameters to see whether results change. In the case of 3i Atlas, such tests do not remove the residual pattern. Statistical treatment of the data is central to confidence assessment. Each measurement is assigned an uncertainty estimate based on signal-to-noise ratio and calibration quality. These uncertainties define weights in orbital fitting. Measurement with smaller uncertainties influence the fit more strongly. If uncertainty estimates are too optimistic, the fit may appear worse than it truly is. Analysts therefore examine the distribution of residuals relative to stated uncertainties. A consistent pattern of residuals larger than expected would suggest underestimated errors. For 3i Atlas, the residuals are comparable to the stated uncertainties, but their coherence stands out. Cross-validation provides an additional check. Independent surveys and telescopes observe the object when possible. Agreement between independent measurements increases confidence that the signal is real. Disagreement prompts investigation. For 3i Atlas, measurements from different instruments show similar deviations when reduced to a common frame. This convergence does not prove a physical cause, but it reduces the likelihood of a single instrument bias. Monte Carlo simulations are used to explore uncertainty space. Synthetic data sets are generated by perturbing the measured positions within their uncertainties. Orbits are fitted to each synthetic data set, producing a distribution of possible trajectories. If the observed deviations are common across many simulations, they may arise from noise. If they appear rarely, they suggest an underlying effect. In this case, the simulations show that while some deviation patterns can arise by chance, the specific persistence observed is less common. Another aspect of confidence lies in historical performance. The same instruments and pipelines have tracked many objects with well-known orbits. Their residual patterns for those objects are examined for comparison. If similar coherent residuals appear frequently without physical explanation, confidence in the current signal would be reduced. For the instruments observing 3i Atlas, such patterns are uncommon but not unprecedented. Analysts also consider selection effects. Objects that draw attention are often those that appear unusual early on. This introduces a bias towards scrutiny of outliers. Some of these outliers later converge toward normal behavior as data improve. Awareness of this tendency tempers interpretation. The goal is not to confirm novelty but to assess it impartially. Confidence is further shaped by temporal coverage. A short observational arc limits the ability to distinguish between competing explanations. As the arc lengthens, some sources of uncertainty diminish. Parallax effects become better constrained. Orbital curvature becomes clearer. Non-gravitational forces, if present, produce cumulative effects that grow relative to noise. At this stage, 3i Atlas remains within an intermediate regime where confidence is sufficient to note deviations but insufficient to attribute them decisively. Language reflects this balance. analysts describe the data as consistent with a small, systematic deviation within current uncertainties. They avoid definitive claims. Reports emphasize what is measured, how it is measured, and what assumptions underlie the analysis. Confidence is expressed numerically where possible and qualitatively where necessary. The inner boundary of this region is marked by a shift in emphasis. Having established that the deviations are unlikely to be purely instrumental, yet not conclusively physical, analysis turns toward enumerating the physical forces that could plausibly act on the object. This transition does not abandon caution. It carries uncertainty forward as an explicit component of all subsequent modelling. Only by understanding confidence can the next inward step, the examination of forces, proceed on firm ground. With confidence bounded and uncertainties carried forward explicitly, attention moves inward to the forces that can act on a small body, travelling through the solar system. At this level, motion is no longer treated as abstract deviation, but as the result of specific physical influences. The starting point remains gravity, the dominant force shaping trajectories on planetary scales. Gravity arises from mass and acts universally, drawing objects toward one another according to distance and mass. For most small bodies, the gravitational pull of the Sun outweighs all other influences by orders of magnitude. In orbital calculations, gravity from the Sun is treated as the primary term. Contributions from planets are added as perturbations, especially from massive bodies such as Jupiter and Saturn. These perturbations are well characterized and can be calculated precisely when the positions of the planets are known. For 3I Atlas, no close planetary encounters are evident within the observed arc, so planetary perturbations remain smooth and predictable. They cannot by themselves account for small systematic residuals that do not align with known perturbative patterns. Beyond gravity, attention turns to weaker forces that act continuously over time. Solar radiation pressure is one such force. Photons carry momentum, and when they strike an object, they impart a small push away from the Sun. The magnitude of this force depends on the object's cross-sectional area, relative to its mass as well as its reflectivity. For large, dense bodies, radiation pressure is negligible. For very small or low-density objects, it can produce measurable effects. Radiation pressure acts radially away from the Sun, and its influence decreases with the square of distance. In the case of 3I Atlas, the observed deviations do not align cleanly with a purely radial force. This does not exclude radiation pressure entirely, but it constrains its role. To produce the observed effect, the object would need an unusually high area to mass ratio. Such a property would imply either extreme thinness or very low density. While not impossible, such characteristics would place the object at the edge of known small body populations. Thermal forces form another category. When an object absorbs sunlight, its surface heats unevenly depending on rotation shape and material properties. As the surface cools, it emits thermal radiation. This emission carries momentum, producing a small force known as a thermal recoil effect. Over long periods, such forces can alter orbits measurably. The most studied example is the Yarkovsky effect, which acts primarily on rotating asteroids and can cause gradual changes in their semi-major axes. Thermal forces depend on factors that are not directly observable in early data, such as rotation rate, spin, axis, orientation, surface conductivity, and roughness. Their effects are usually small and accumulate slowly. For near-Earth asteroids, they are detectable only after years of precise tracking. For an object like 3I IATLAS observed over a relatively short time span, thermal forces would need to be unusually strong to produce noticeable deviations. This possibility is examined cautiously, recognizing both the uncertainties involved and the lack of direct evidence. Outgassing represents a more familiar non-gravitational force in cometary dynamics. As volatile materials sublimate, escaping gas produces a reaction force on the nucleus. This force can accelerate the object in directions that depend on the location of active regions and the object's rotation. Outgassing forces often vary with distance from the Sun, increasing as heating intensifies. They can also vary irregularly if activity turns on or off. For many comets, outgassing is accompanied by visible signs such as a coma or tail. However, low-level outgassing can occur without producing easily detectable dust. Gas species that do not condense into visible particles may escape invisibly. In such cases, the force can still alter motion slightly. The absence of visible activity in 3I Atlas therefore limits but does not eliminate outgassing as a candidate force. The directionality of outgassing forces is complex. They're not necessarily radial. Depending on surface geometry and rotation, the net force can act along or against the direction of motion, or even perpendicular to it. Modeling such forces requires assumptions about surface properties that cannot yet be tested. Analysts therefore explore parameterized models testing whether plausible outgassing scenarios could reproduce the observed residuals without contradicting other constraints. Interactions with the interplanetary medium are also considered. The solar system is filled with the tenuous plasma known as the solar wind, composed of charged particles streaming outward from the Sun. For large bodies, its effect is negligible. For very small particles, it can be significant. The coupling depends on electrical charge size and mass. For an object of uncertain size like 3I Atlas, the effect is expected to be minimal, but it is included in comprehensive force inventories. Tidal forces are another category arising from differential gravity across an object's extent. These forces become important during close approaches to massive bodies. They can alter rotation states or even disrupt fragile objects. In the observed trajectory of 3I Atlas, no close tidal encounters occur within the current data window. Tidal forces therefore do not contribute meaningfully to the observed deviations. Relativistic corrections are applied routinely in high-precision orbital calculations. These corrections account for effects predicted by general relativity, such as the curvature of spacetime near massive bodies. For small bodies at typical solar system distances, relativistic effects are extremely small. They are included for completeness but do not explain residuals of the observed magnitude. Each force considered carries characteristic signatures in direction, magnitude, and dependence on distance. Analysts compare these signatures with the pattern of deviations seen in the data. No single force provides a perfect match at this stage. Gravity alone is insufficient. Radiation pressure appears misaligned. Thermal forces are plausible, but require assumptions that cannot yet be verified. Outgassing remains a candidate but lacks supporting observational evidence. The purpose of this inventory is not to select a favored explanation, but to delimit the space of possibilities. Forces that can be ruled out are set aside. Those that remain are carried forward into more detailed modelling as data improve. Throughout this process, restraint is maintained. The presence of unexplained residuals does not imply the presence of unknown physics. It indicates only that known forces may be acting in ways not yet fully constrained by observation. As this region concludes, the object stands under the influence of many small forces layered atop gravity. None dominates decisively. The path forward lies in narrowing these possibilities by examining specific classes of non-gravitational effects in greater detail. The next inward step focuses on those effects that, while subtle, have the potential to produce motion that departs from expectation without leaving obvious visible traces. Among the forces considered, non-gravitational effects warrant focused attention, because they can operate subtly, persistently, and without dramatic visual signatures. These effects occupy a narrow space between well-modelled gravity and speculative mechanisms. They are grounded in established physics, yet their expression depends sensitively on properties that are difficult to observe directly. For 3I Atlas, this category offers plausible pathways by which small but systematic deviations could arise. Outgassing remains the most familiar non-gravitational mechanism. In icy bodies, volatile substances transition from solid to gas when heated. The escaping gas exerts a reaction force on the body, altering its motion slightly. The magnitude of this force depends on the rate of mass loss and the velocity of the escaping gas. In classical comets, outgassing produces visible comae and tails composed of gas and dust. However, not all volatile species produce dust, and not all dust is easily detected at large distances or low production rates. Gas species such as carbon monoxide or molecular nitrogen can sublimate at relatively low temperatures and may escape without entraining significant dust. In such cases, the object may appear inert in optical images while still experiencing a measurable force. The direction of this force depends on where the gas escapes from the surface and how the object rotates. If active regions are localized, the net force can be offset from the Sun-object line and may vary with rotation period. For 3I Atlas, no direct spectral evidence of gas emission is available in the early observations. The object is faint and survey instruments are not optimized for detailed spectroscopy. This absence of evidence does not rule out low-level outgassing. It places an upper bound on dust production, but leaves gas production largely unconstrained. Analysts therefore consider whether a gas-driven acceleration of the observed magnitude could occur without violating brightness limits. Thermal recoil forces form a second class of non-gravitational effects. When an object absorbs sunlight, its surface temperature rises. As it rotates, different regions heat and cool at different times. The delayed re-emission of thermal radiation produces a net force that depends on the rotation state and surface properties. This effect is directional and can either increase or decrease orbital energy over time. It is sensitive to parameters such as rotation period obliquity, thermal inertia, and surface roughness. In known asteroids, thermal recoil effects accumulate over long timescales and are detected through careful tracking over years or decades. For a newly discovered object with a short observational arc, detecting such effects would be unusual unless the object has extreme properties. A very small size, low density, or unusual surface composition could amplify the effect. These possibilities are explored through modelling, but they remain speculative without independent constraints on physical properties. Another non-gravitational influence arises from radiation pressure modified by shape and orientation. While radiation pressure itself acts radially, an irregularly shaped object can experience torques that alter its rotation state. Changes in rotation can in turn modulate thermal recoil forces. This coupling between radiation pressure rotation and thermal emission creates a complex dynamical system. For most objects, the net effect is small, but in marginal cases it can become detectable. Electrostatic effects are considered briefly. Small bodies can accumulate electrical charge through interactions with solar radiation and the solar wind. In principle, Charged particles interacting with magnetic fields could experience forces. In practice, for macroscopic bodies, such effects are negligible compared with gravity and radiation pressure. For 3, I-Atlas electrostatic forces are dismissed as insignificant within current understanding. Mass loss through processes other than classical sublimation is also examined. Thermal fracturing or desorption of surface materials could release small amounts of gas or dust. Such processes might occur without producing a sustained coma. Their contribution to non-gravitational acceleration would be intermittent and likely small. Without observational evidence, they remain secondary considerations. The direction and temporal behavior of the observed deviations provide partial guidance. If non-gravitational forces are at work, their effect should correlate with solar distance or orientation. Analysts look for trends in residuals as the object moves closer to or farther from the Sun. At this stage, the data span a limited range of distances, making trend detection difficult. No strong correlation is yet established. Parameter estimation techniques are applied to test whether adding a non-gravitational term to the orbital model improves the fit. Such terms are typically expressed in simplified forms representing acceleration components along radial transverse and normal directions. By fitting these parameters alongside gravitational ones, analysts assess whether the data favor their inclusion. For 3I-Atlas, introducing a small transverse acceleration can reduce residuals modestly. The improvement is statistically marginal but consistent across independent data sets. This result is treated cautiously. Adding parameters always improves fit to some degree. The question is whether the improvement exceeds what would be expected from chance, given the additional freedom. Statistical criteria are applied to guard against overfitting. In this case, the evidence suggests that a non-gravitational term is permissible, but not required by the data. Comparisons with other objects provide perspective. Some comets exhibit non-gravitational accelerations of similar magnitude without obvious activity early on. In those cases, activity often becomes visible later as the object approaches the Sun. Other objects initially suspected of non-gravitational behavior later conform to gravitational models as uncertainties shrink. The current state of 3I-Atlas resembles the early phase of both categories. The language used to describe these effects remains precise. Analysts state that non-gravitational effects cannot be excluded and that certain models can account for the observed deviations within uncertainty limits. They avoid statements that imply certainty or novelty. The focus remains on compatibility rather than explanation. As observations continue, the role of non-gravitational effects will either strengthen or diminish. If deviations grow in magnitude or show clear dependence on solar distance models, involving outgassing or thermal forces will gain support. If deviations fade as the orbit is refined, simpler explanations will prevail. At present, the non-gravitational hypothesis occupies a narrow but defensible position. The inward movement through this region brings the analysis closer to the object itself. Forces act on mass area and structure. To understand why a given force might matter, one must consider what kind of object is being acted upon. The next step, therefore, shifts focus from forces in isolation to the physical properties of 3I-Atlas that determine how those forces would manifest, drifts inward away from telescopes and orbital charts, and into the quiet machinery of interpretation where numbers are asked to mean something without being allowed to imagine. The object still called 3I/Atlas continues its passage through the inner solar system, and the data continues to arrive in small, careful parcels, astrometric points, brightness curves, residuals that refuse to flatten completely. In the control rooms and offices where this information is examined, no one speaks of intent, yet the word hovers at the edge of the conversation like a shadow cast by a moving hand. What unsettles the analysts is not speed alone nor the slight non-gravitational acceleration that persists after accounting for solar radiation pressure and outgassing models, but the coherence of the deviations. They do not scatter randomly, they cluster. The residuals bend in the same direction across multiple observation windows, as if the object is not merely reacting but maintaining a preference. In classical celestial mechanics, preference is an illusion. Forces act, bodies respond, and patterns emerge without awareness. Yet here the pattern feels sustained, and sustainability is what draws the human mind toward agency, even when it knows better. The calculations are rerun assumptions stripped down to their bones. Could asymmetric outgassing explain it, a jet of sublimating material venting more strongly from one hemisphere than another? Possibly, but the thermal models demand a composition that should have revealed itself spectroscopically by now. Could it be radiation pressure acting on an unusually thin, elongated structure? That too is tested, and while it fits part of the curve, it fails to account for the stability of the orientation implied by the acceleration vector. Orientation, after all, is hard to keep without some form of spin control, and spin control belongs to objects that either tumble chaotically or regulate themselves. Light curves are examined for periodicity, and they show hints faint and inconsistent like a rhythm heard through walls. Nothing conclusive, nothing publishable as evidence of design, yet enough to prevent the mind from resting. The role of the scientist here is not to chase wonder, but to restrain it, to stand guard at the border between anomaly and narrative. Every anomalous interstellar visitor before this one eventually surrendered to a mundane explanation, and history presses its hand heavily on the present, reminding everyone how easily novelty masquerades as mystery. Still, the object's trajectory continues to thread improbably through observational constraints, passing close enough to be studied, yet fast enough to limit prolonged scrutiny, as if it is borrowing the solar system briefly and with purpose, before returning to the dark between stars. In meetings, the language stays cautious. Terms like consistent acceleration and persistent vector are chosen precisely because they do not imply motivation. Yet outside the formal record, in the private space between thought and breath, a quieter question forms. What does it mean for matter to behave as though it has a plan? Physics insists that plans are stories told by nervous systems, not by rock and ice, and this insistence has served humanity well. It keeps equations honest and telescopes pointed correctly. But the human brain is a pattern recognition instrument evolved under uncertainty, and when it encounters sustained regularity in an unfamiliar context, it does what it has always done: it listens more closely. Section 10 lingers on this, listening on the discipline required to hear without inventing, to acknowledge discomfort without filling it. The analysts double-check their role as observers, not protagonists as recorders, not interpreters of cosmic intention. They remember that interstellar space is not empty but textured, filled with gradients of dust, magnetic fields and radiation that can sculpt motion in ways still imperfectly understood. They remind themselves that the universe has no obligation to feel intuitive, and yet as nights pass and new data aligns with old anomalies, instead of erasing them, the unease becomes quieter but deeper, like a low-frequency hum beneath thought. There is also a historical echo here, a memory of past moments when human certainty had to widen its frame, when planets refused to move in perfect circles, When Mercury's orbit bent slightly wrong, when galaxies spun too fast for the matter they seemed to contain. Each time the answer was not intention, but a deeper law, invisible until named. This memory offers comfort, suggesting that 3I/Atlas may be another doorway to understanding rather than a messenger with a message. Still, the mind notes how the object's path minimizes chaotic encounters, how it threads gravitational wells without excessive deflection, how its acceleration, whatever its cause, does not spin it wildly, but keeps it oriented long enough to be measured. None of this proves anything beyond the extraordinary adaptability of natural processes, yet the impression remains subtle and persistent that the object is doing more than falling. In the quietest hours, some researchers admit to feeling watched not by the object itself, but by the implications of their own thoughts, aware that curiosity can slide into projection if left unattended. So they slow down, returning to first principles, recalibrating instruments, inviting independent teams to challenge their assumptions. This too is part of the ritual that keeps science from becoming myth. The section closes not with an answer, but with a posture attentive, restrained, awake. 3. I/Atlas continues on its way indifferent to the meanings ascribed to it, while those who study it practice the difficult art of holding mystery without naming it. In that space between what is measured and what is felt, the universe remains vast and patient, allowing humans to glimpse patterns that look just for a moment like intent, before dissolving back into motion governed by laws still unfolding, turns its attention to the human reflex that emerges when uncertainty lasts too long. The quiet shift from analysis to interpretation that happens not in press releases but in the private architecture of thought. By now 3, I/Atlas has been observed long enough that its behaviour can no longer be dismissed as a transient glitch in early data, yet not long enough to be comfortably categorized. It occupies an uncomfortable middle ground where explanation exists, but does not fully settle, and it is precisely in this space that the discipline of science is most severely tested. The role must be checked again and again, observer, not narrator, measurer, not meaning maker. Still, the brain shaped by millions of years of survival does not like prolonged ambiguity. In nature, sustained patterns often meant something important: a predator's route, a season's return, the deliberate movement of another mind. The unease surrounding 3I/Atlas is not that it breaks known laws outright, but that it seems to skirt their edges with too much consistency. In statistical terms, the probability distributions are odd but not impossible. In psychological terms, they are provocative. This section explores how easily the language of intent can creep in, not because scientists are careless, but because they are human. Papers remain precise, filled with caveats and confidence intervals, yet conversations soften after hours, metaphors slipping through where equations leave off. Someone says the object prefers a trajectory, another jokes that it is behaving itself, and everyone understands that these are figures of speech, harmless shorthand. And yet figures of speech are powerful. They train intuition, and intuition once trained quietly influences where attention lingers. The danger is subtle, not believing the object has intent, but letting that possibility shape which explanations feel satisfying. Section 11 slows down here, examining how the scientific method was designed to guard against exactly this drift, and how it sometimes struggles when faced with phenomena that are rare, fleeting, and fundamentally unrepeatable. Interstellar visitors do not offer controlled experiments. They arrive without warning, move quickly, and leave forever, taking their full context with them. There is no second chance to adjust instruments or test alternative hypotheses under identical conditions. This asymmetry places unusual weight on interpretation, and interpretation is where bias can hide. To counter this, teams begin to formalize what was once informal, creating checklists not just for data quality, but for language itself. Drafts are read for anthropomorphic leakage. Phrases implying choice or strategy are excised, replaced with colder terms: vector persistence, torque, stability, acceleration, consistency. This self-policing is not censorship, but hygiene, a way of keeping the role intact. Yet even as the language is scrubbed, the data remains quietly strange. Models invoking exotic but natural explanations grow more elaborate hydrogen icebergs that sublimate in visibly fractal dust, aggregates with extreme area-to-mass ratios, magnetic interactions with the solar wind acting on charged surfaces. Each model can explain part of the behavior, sometimes most of it, but rarely all of it, without fine-tuning. Fine-tuning is not forbidden in physics, but it raises eyebrows, especially when it must be invoked repeatedly. The object seems to require just the right properties to remain ordinary, and ordinariness under such conditions begins to feel fragile. Section 11 does not argue that this fragility implies design. Instead, it observes how fragile explanations prompt the mind to reach for alternatives even when those alternatives are explicitly rejected. There is also a cultural layer at work. This is an era saturated with stories of probes, signals, and artificial visitors, and no scientist operates in a vacuum free of narrative influence. The role demands awareness of this background noise, the ability to distinguish between what the data suggests and what the imagination supplies uninvited. Some researchers deliberately step back, handing analysis to colleagues less emotionally invested, knowing that distance can sharpen clarity. Others immerse themselves deeper, trusting that familiarity will dissolve mystery rather than amplify it. Both approaches are valid and both reveal something about how humans cope with the unknown. Meanwhile, 3I/Atlas continues to recede from the sun, its brightness diminishing its signal to noise ratio slipping toward the threshold, where interpretation becomes guesswork. There is a quiet urgency now, not panic, but an awareness that the window is closing. Every additional data point feels precious, not because it might confirm something extraordinary, but because it might finally allow the ordinary to assert itself cleanly. And yet, even as the object fades, the questions it raised do not. They migrate inward away from this specific visitor and toward a broader reconsideration of assumptions. How many interstellar objects pass unnoticed because they behave exactly as expected? How many anomalies have been smoothed over by noise thresholds and model choices? Section 11 suggests that the true impact of 3I/Atlas may not lie in what it is, but in how it sharpens awareness of what observers bring with them when they look. The role of science is not only to describe the universe, but to discipline the observer to refine perception until it can tolerate uncertainty without rushing to closure. In this sense, the object becomes a kind of mirror reflecting back the limits of current frameworks and the psychological contours of those who use them. The section lingers on this reflection, on the quiet humility required to admit that not knowing is not a failure but a state. As the data stream thins and the object slips beyond practical reach, the temptation is to summarize, to declare provisional conclusions and move on. But Section 11 resists that impulse, ending instead with an open stance. 3I/Atlas does not need to be intentional to be instructive. Its value may lie in how it exposes the thin line between explanation and story, and how carefully that line must be guarded. The universe, indifferent and vast, continues to offer phenomena that sit just beyond the comfort zone of existing knowledge. The task is not to tame them with premature meaning, but to let them unsettle, gently, expanding the space in which understanding can eventually grow. Moves inward from the human tendency to interpret toward the institutional systems that absorb uncertainty and attempt to stabilize it. At this stage, the focus is no longer on individual observers or private intuition, but on how scientific communities collectively respond when an object resists clean classification. The presence of 3i Atlas within formal channels begins to change in tone as it ages. Early alerts give way to technical circulars, then to archival status. This transition is procedural, yet it carries meaning in how attention is allocated. Observatories operate under constraints of time, funding, and competing priorities. When an object no longer promises decisive clarification, it must justify continued observation against countless other targets. Section 12 examines how that justification unfolds not as drama, but as process. Committees review proposals weighing incremental gains against opportunity costs. Models are updated with diminishing returns, each new fit narrowing uncertainties by small margins rather than resolving them outright. The role remains constant measure, compare, report. But the context shifts from discovery to accounting. This is where anomalies often settle into the background, not because they are resolved, but because they become familiar. Familiarity dulls urgency. The object is no longer new, and novelty, though officially irrelevant, plays a quiet role in sustaining attention. Section 12 stays with this phase, describing how data pipelines incorporate the object into long-term data sets, how its parameters are averaged, smoothed, and eventually folded into population statistics. Interstellar visitors cease to be singular events and become entries in a growing, though still sparse, category. This inward movement highlights a subtle transformation. What was once a challenge to understanding becomes a test of infrastructure. Are current survey strategies adequate to catch such objects early? Are cadence and sensitivity tuned to behaviors that do not conform to cometry norms? These questions are operational, not philosophical, and they drive concrete changes. Software thresholds are adjusted. Alert systems are retrained on expanded definitions of outgassing and non-gravitational acceleration. None of this implies that 3i Atlas is exceptional in origin. Rather, it acknowledges that existing filters were designed around expectations shaped by the solar system alone. Section 12 emphasizes that adaptation does not require belief in anything extraordinary. It requires only the recognition that the environment has broadened. As interstellar objects become a recognized class, however small, they force a recalibration of baselines. What counts as normal must expand. This expansion proceeds cautiously, guided by consensus and review. Draft papers circulate with language that is deliberately restrained, stripping away earlier metaphors until only parameter space remains. Acceleration vectors are reported with uncertainties spelled out. Surface interaction hypotheses are ranked by plausibility without narrative flourish. The discipline here is collective. Individuals may feel curiosity or even unease, but the system absorbs those emotions and outputs tables, figures, and archived files. Section 12 observes how this absorption can feel anticlimactic, yet it is precisely what allows science to function over long timescales. Objects pass, but frameworks endure. Still, endurance has a cost. By smoothing anomalies into categories, sharp edges are lost. The peculiarities of 3i Atlas become averages, its most distinctive behaviors diluted among error bars. This is not a flaw so much as a trade-off. To build a coherent picture of interstellar populations, individual strangeness must be subordinated to statistical coherence. Section 12 lingers on this tension, noting that some features resist easy averaging. Certain rotational properties, for example, remain poorly constrained because observations were sparse during critical phases. Surface composition indicators inferred indirectly carry assumptions that cannot be tested once the object fades beyond reach. These gaps are recorded flagged and then carried forward as uncertainties. They do not disappear, but they also do not halt progress. The system is designed to move despite incompleteness. As the section continues, inward attention turns to how results are communicated outward to funding bodies, educators, and the public. Language is filtered again, this time for clarity rather than bias. The phrase intent is carefully avoided, replaced with formulations emphasizing unknown mechanisms. Press summaries highlight what is learned rather than what remains puzzling. This is not deception, but stewardship, an effort to prevent speculation from outpacing evidence. Yet even here, traces of the original discomfort remain. Questions from outside the field often circle back to the same point: why does it look that way? The answer, repeated patiently, is that appearance can mislead, and that physics often produces counterintuitive results. Section 12 does not argue that this reassurance is sufficient, only that it is necessary. The role requires maintaining boundaries between what can be said responsibly and what can be imagined freely. Within those boundaries, work continues. Archival studies re-examine older data sets, searching for overlooked interstellar candidates that behaved quietly without drawing notice. Simulations grow more detailed, exploring ranges of material properties that were once considered unlikely. Each adjustment is small, inward, technical. There is no dramatic pivot, only accumulation. The section underscores that this is how knowledge expands in practice, not through singular revelations, but through the steady accommodation of edge cases. As 3I Atlas recedes into the statistical background, its immediate mystery softens, but its influence persists in these adjustments. It becomes part of the scaffolding rather than the centerpiece. Section 12 remains careful not to frame this as resolution. The object has not been explained away, it has been contextualized. Context reduces shock but preserves uncertainty. The final movement of the section brings attention to archival permanence. Data related to 3 Atlas is stored indexed and made available for future reanalysis. This is an inward turn toward time itself, acknowledging that understanding is not bound to the moment of observation. New techniques not yet conceived may one day extract patterns that current tools cannot. The role extends across generations, trusting that restraint now enables insight later. Section 12 ends in this quiet posture where the object is no longer present, but its trace remains embedded within systems designed to remember without embellishment. The universe continues to deliver inputs that strain expectation, and the response, institutional and measured, is to widen the frame just enough to hold them without rushing to conclusions or retreating into familiarity. In this holding, science maintains its balance, neither denying anomaly nor surrendering to it, but carrying it forward as part of an ever-deepening record, moves further inward away from institutions and archives and toward the physical constraints that ultimately bound interpretation. At this depth, attention returns to matter itself, not as theory or category, but as substance responding to forces. Whatever 3I Atlas is, its behavior must emerge from interactions between material properties and environment. This section stays close to those interactions, narrowing focus to the smallest scales that can still be inferred from distant observation. The object travels through a region dominated by sunlight, solar wind, and the weak but persistent pull of gravity. Each of these influences acts continuously, without preference or intention. The question is not why the object behaves as if guided, but how simple forces acting on unusual materials can produce trajectories that appear structured over time. Section 13 examines the limits of what can be deduced when direct sampling is impossible. Surface composition is inferred from reflected light, its spectrum flattened and blurred by distance and motion. Small deviations hint at organics, ices, or dust, but none resolve cleanly. The absence of a visible coma suggests either a lack of volatile material or a mode of release that does not produce large particles. Models explore both. One class of explanations considers extremely porous structures, aggregates so loosely bound that individual grains respond to radiation pressure almost independently. In such a body, sunlight does not merely warm the surface, but penetrates, redistributing momentum across a broad area. The resulting acceleration can be smooth and sustained, lacking the jets and asymmetries typical of comets. Another class considers surfaces coated with materials that sublimate without producing detectable dust, such as molecular hydrogen or nitrogen under specific conditions. These substances, if present in sufficient quantity, could generate thrust while remaining invisible to telescopes tuned for heavier molecules. Section 13 does not privilege one model over another. Instead, it traces their shared constraint. All require properties that are rare but not forbidden. Rarity is uncomfortable but not disqualifying. Interstellar space is vast, and processes operating over billions of years can produce outcomes seldom encountered locally. The inward movement of this section emphasizes scale. What seems finely tuned at the level of one object may be statistically inevitable across a galaxy. Still, the models strain against observational limits. Many require initial conditions that cannot be confirmed, such as formation environments richer in certain volatiles than those typically observed. These environments may exist around other stars, but evidence remains indirect. Section 13 stays with this uncertainty, noting how it narrows but does not close explanatory space. Rotation adds another layer. Light curves suggest complex tumbling rather than simple spin, implying an irregular shape or heterogeneous mass distribution. Tumbling bodies dissipate energy over time, tending towards stable rotation states. That three-eye atlas maintains complexity for as long as it is observed, constrains internal damping. Either the object is rigid enough to resist rapid settling, or its shape redistributes stresses in ways that prolong motion. Both possibilities point to unusual internal structure. Again, unusual does not mean artificial. Nature produces extremes when given enough time and material. Section 13 brings attention to thermal behavior. As the object approaches and recedes from the sun, temperature gradients develop across its surface. Expansion and contraction induce stresses, potentially opening microfractures that release trapped gases or rearrange surface layers. Such processes can be gradual and symmetric, avoiding the dramatic signatures associated with cometary outbursts. The resulting forces may align closely with the object's velocity vector, producing acceleration that appears purposeful when viewed at coarse resolution. At finer resolution, it remains the sum of countless small interactions, none of which imply direction beyond local physics. The section emphasizes that purpose is a projection applied after the fact, not a property required by the equations. Still, equations alone do not settle intuition. The inward journey continues by examining limits imposed by measurement itself. Astrometry relies on precise timing and position, but small errors accumulate. When signals weaken, assumptions fill gaps. Noise can mimic pattern, and pattern can persist long enough to invite interpretation. Section 13 carefully distinguishes between persistence arising from physical cause and persistence arising from correlated uncertainty. Analysts model both comparing outcomes to ensure that the observed acceleration exceeds what error alone would produce. In the case of 3I Atlas, it appears to do so, but margins are slim. This slimness matters. It defines how confident one can be without overstepping. The role demands restraint precisely here at the boundary, where data thins and inference grows heavier. Section 13 also addresses energy budgets. Any sustained acceleration must draw from an energy source. Sunlight provides ample energy, but coupling efficiency depends on surface properties. Calculations show that even small efficiencies, if applied over large areas, can yield measurable effects. This reframes the problem. Instead of asking what exotic engine might drive the object, the focus shifts to how effectively ordinary energy can be harnessed by uncommon forms. Thin sheets, fluffy aggregates, and layered ices all behave differently from solid rock. Interstellar travel itself may favour such forms as denser bodies collide and fragment over time. Survivors may be those light enough to be nudged rather than shattered. Section 13 lingers on this possibility not as conclusion but as context. The object that arrives is not a random sample of all that exists but of what endures. As the section approaches its deepest point, it acknowledges what cannot be known. Without proximity, internal composition remains speculative. Without repetition, behaviour cannot be tested under varied conditions. The inward path ends not in certainty but in boundary. Physics provides constraints, not stories. Within those constraints, multiple configurations remain viable. Section 13 holds this multiplicity without resolving it, emphasizing that explanation does not require singularity. Several ordinary processes can overlap to produce behavior that feels coordinated when viewed from afar. The sense of intent dissolves as scale contracts replaced by gradients, stresses and forces acting without awareness. The section closes by reaffirming the role to describe how matter behaves under given conditions and to stop where description ends. Beyond that boundary lies imagination, valuable in other contexts but not here. 3. I Atlas, reduced to materials and forces, remains unusual, yet bounded, its apparent coherence emerging from interaction rather than direction. In this inward stillness, the object is no longer a question about purpose, but a reminder of how complex outcomes can arise from simple rules applied over long distances and deep time, moves inward again, narrowing from material behaviour toward the boundary, where observation, modelling and expectation converge. At this depth, the object itself is no longer the sole focus. Attention shifts to the frameworks that translate raw measurements into motion, mass and cause. These frameworks are mathematical, but they are also historical, shaped by decades of solar system study, where most small bodies conform within tolerance to a limited set of behaviours. 3I Atlas presses against those tolerances. This section remains with that pressure, examining how models bend before they break, and how far they can be stretched without losing reliability. Orbital solutions begin as equations of motion, integrating gravitational influences from the Sun and planets. Non-gravitational terms are added only when residuals persist, when predicted positions drift systematically from observations. In comets, these terms are linked to outgassing parameterized in ways that assume symmetry locality and volatility tied to temperature. Applying these same terms to an interstellar object is an act of convenience, not conviction. Section 14 slows, here noting that convenience can quietly harden into assumption if left unexamined. For 3, IATLAS standard cometry models reduce residuals but do not eliminate them cleanly. Adjustments are made, coefficients allowed to vary, functional forms modified. Each adjustment improves fit but also distances the model from its physical roots. The danger is not error but overfitting, where a model explains the past at the expense of predictive meaning. This inward movement highlights a core discipline of science, the willingness to accept imperfect fits rather than force coherence where none exists. Section 14 describes how alternative modelling approaches are tested alongside traditional ones. Radiation pressure models treat the object as having an effective area-to-mass ratio, a single parameter encapsulating shape, density, and reflectivity. Such models can reproduce smooth accelerations without invoking mass loss. However, they require ratios higher than those typical of asteroids, implying either extreme thinness or extreme porosity. These implications are noted, not dramatized. They sit within the model as consequences, not claims. Competing teams run independent fits, blind to one another's assumptions, comparing outcomes only after results stabilize. Convergence is partial. Some parameters align, others diverge. Section 14 remains with this divergence, emphasizing that disagreement at this level is not failure, but signal. It marks where data resolution meets conceptual boundary. As the section moves deeper, it considers time. Observations span weeks to months, a short interval against the object's long journey. Models extrapolate backward and forward, reconstructing inbound paths and projecting outbound futures. Small uncertainties grow rapidly over these spans. A tiny misestimate in acceleration compounds into large positional differences. Section 14 underscores how this sensitivity limits confidence. Claims about origin regions or formation environments become probabilistic, not declarative. The role requires stating this plainly, resisting the urge to narrate a singular past. The inward turn continues by examining the instruments themselves. Telescopes have biases shaped by design. Survey instruments favor motion against star fields, certain brightness ranges, certain speeds. Objects that move too slowly or too fast may evade early detection. 3i Atlas is found within these constraints, not outside them. Its discovery reflects both its properties and the filter through which it is seen. Section 14 stresses that this filter must be accounted for when interpreting rarity. An object that appears unique may simply be the first of its kind, detectable under current conditions. This is not speculation, but statistical caution. The section then looks at simulation ensembles where thousands of hypothetical objects with varied properties are propagated through solar system models to see which would be noticed. In these ensembles, objects like 3i Atlas appear infrequently, but not vanishingly so. Their existence does not require extraordinary origins, only wide distributions. The inward movement here is subtle. It replaces singular mystery with population thinking. Individual oddity dissolves into tail behavior. Still, tails matter. They define the limits of expectation. Section 14 also addresses communication between modelers and observers. Data reduction choices affect fits and fits influence which data points are weighted or discarded. This feedback loop is managed through protocols designed to minimize bias, but it cannot be eliminated entirely. Awareness of the loop is part of the role. Teams document assumptions explicitly allowing later reanalysis. Section 14 notes that this documentation is often the most valuable legacy of such objects, more enduring than any single conclusion. As the section approaches its inner boundary, it confronts the question of sufficiency. At what point is an explanation good enough? Science does not require completeness, only adequacy within stated limits. For 3, the Atlas. Several models meet this standard. None require intent. None violate known physics. Each leaves residues of uncertainty that cannot be resolved without new data. Section 14 holds these residues without attempting to dissolve them. It emphasizes that restraint here preserves credibility. Overreach would erode trust more than ambiguity. The inward journey ends with a quiet recalibration. The object is no longer framed as behaving strangely, but as revealing the edges of existing tools. Those tools are refined incrementally informed by this encounter. In that sense, 3I Atlas functions as a calibration point rather than a message. The universe supplies such points irregularly without regard for readiness. The role is to absorb them, adjust, and proceed. Section 14 closes in this adjusted state, where models are slightly broader expectations, slightly looser, and the boundary between known and unknown more clearly traced, not crossed, completes the inward path, arriving at the quiet core where uncertainty is no longer something to be reduced, but something to be carried correctly. At this depth, there is little left to adjust in models or reinterpret in data. What remains is the discipline of stance. The Object 3I Atlas has passed through observation interpretation, institutional processing, material analysis, and modeling constraint. Each layer has narrowed possibilities without closing them. Section 15 stays with this narrowing not to resolve it, but to clarify what resolution would mean and what it would not. In science, closure is often mistaken for explanation, yet explanation can exist without finality. The role here is not to decide what the object is in any absolute sense, but to define the space within which it can be understood without distortion. That space is now well bounded. 3I Atlas is an interstellar object, its trajectory consistent with origin beyond the solar system. Its motion includes measurable non-gravitational components. Those components can be modelled using known physical mechanisms acting on uncommon but plausible material configurations. None of these statements require embellishment. None imply agency. Section 15 emphasizes that this sufficiency is not diminished by the persistence of uncertainty. Uncertainty is not residue, it is structure. It marks where knowledge ends and assumption would begin. Maintaining that boundary is part of the role. As the inward focus settles, attention turns briefly to comparison. Previous interstellar visitors differed markedly from 3I Atlas in brightness evolution morphology and inferred composition. That diversity itself is informative. It suggests that interstellar space does not deliver uniform samples, but a wide spectrum shaped by formation collision and erosion processes across many stellar environments. The solar system is encountering only a thin slice of that spectrum. Each arrival adds texture, not narrative. Section 15 resists the temptation to frame this sequence as progression. There is no arc, no build-up toward revelation. There is only accumulation. The inward movement continues by addressing the phrase that clings to the object in informal discourse, the sense that it is acting with intent. Section 15 dismantles this phrasing carefully, not by dismissal, but by relocation. Intent belongs to systems that represent goals and adjust behavior to achieve them. No evidence of such representation exists here. What exists are forces applied consistently over time, producing smooth outcomes. Human cognition is tuned to detect agency because it mattered for survival. That tuning does not deactivate in scientific contexts. The role requires recognizing when it is triggered and setting it aside. Section 15 treats this not as weakness but as condition. The fact that intent is perceived at all says more about the observer than the object. As the inward path reaches its terminus, the narrative slows further. There's no new data arriving. The object is gone, its signal fallen below thresholds, its path continuing silently through interstellar space. What remains is record. Record is inert, but interpretation of record is active. Section 15 emphasizes that future reinterpretation is expected, not exceptional. As instruments improve and theories mature, archived data may yield new constraints. Alternatively, it may remain exactly as it is, a snapshot of a moment when understanding paused at a boundary. Both outcomes are acceptable. The role does not demand productivity from every anomaly. Sometimes holding is enough. Section 15 also clarifies what this object does not require. It does not require revision of fundamental physics. It does not require new categories of intelligence. It does not require secrecy or suppression. Its strangeness operates well within the elastic range of existing knowledge. That elasticity is often underestimated. Physics accommodates extremes without complaint. The discomfort arises not from violation, but from unfamiliar combination. Section 15 reframes this discomfort as signal not of threat, but of growth. When combinations previously unencountered appear, frameworks must stretch. Stretching is not breaking. The inward journey ends by returning briefly to the role itself. The narrator remains external, descriptive, bounded. There is no claim of significance, no extraction of meaning. The object is not a messenger. It is a participant in a universe governed by interaction, not intention. Section 15 closes with this clarity intact. 3i Atlas is neither ordinary nor extraordinary in any absolute sense. It is specific. Its behavior is the result of conditions acting over long durations in environments far from the solar system. Those conditions are partially known, partially inferred, partially opaque. That mixture is common in astronomy. The task has been to describe it without smoothing it into story or inflating it into symbol. Having moved inward through all accessible layers, there is nowhere further to go without leaving evidence behind. The role stops here. The record stands as it is, precise, incomplete, and sufficient. The wind down begins without transition, easing away from analysis and into a quieter register, while remaining within the same discipline. The object is no longer active in observation or debate. It moves on unmeasured beyond the region where its presence mattered. What stays behind is stillness. Data rests in archives. Models remain open, neither accepted nor rejected beyond their stated bounds. The pace slows naturally when nothing more is demanded. The universe does not require completion. It continues whether understanding advances or pauses. Interstellar space carries countless bodies like 3i Atlas, most unseen. Some briefly noticed, all subject to the same indifferent forces. Their paths cross stars, drift through radiation fields, absorb energy, release it, and change slowly over time. No attention follows them. No record is kept. The one that passed here did so under particular conditions at a moment when instruments were pointed in the right direction. That coincidence is enough to explain why it was seen, and others were not. There is no further implication. As attention recedes, the focus softens toward the broader background in which such events occur. Gravity continues its quiet work. Light travels outward without pause. Matter interacts, rearranges, and disperses. Understanding advances unevenly, sometimes through clarity, sometimes through restraint. The discipline practiced throughout remains applicable beyond this case. Describe what is observed. State what is uncertain. Stop where evidence ends. Rest there. The inward journey has reached its natural limit, not marked by revelation but by calm sufficiency. Nothing is unresolved in a problematic sense. There is only what is known and what is not yet accessible. This balance does not need correction. It needs patience. Over long time scales, patience aligns naturally with sleep. Thought loosens its grip on explanation. Details fade without being lost. The record remains intact even as attention drifts. The universe continues its motion without commentary, and the mind, having traced one small passage through it, is free to let go.